Good morning. Good morning. Welcome to biology. And we're going to review a little bit from the last time. We were talking about the difference between elements and ions. So let's review. Write out for me the notation. How would you write calcium element? How would you write calcium ion? How would you write oxygen as an element and oxide, which is the same thing as oxygen ion? Try that for me right now. We'll go ahead and check your answers with mine. It's okay if you haven't finished yet. But here's my answers. Calcium just as an element or calcium atom is just capital Ca. But calcium ion, remember that's when it either loses or gains electrons. Because it's in column number 2, everyone that we're interested in biology, in column 2 forms a 2+ ion. Oxygen element is just O. Oxide or oxygen as an ion, because it's in column 16, everybody that we're interested in column 16 forms a -2 ion. We're going to practice a little more with our tables today. But let's move on to this sample question. By the way, this is a sample question that you might see on the quiz. You know, writing out which one is calcium element, which is calcium ion, which is oxygen element, which is oxygen ion. So you might simply see something like this on the chapter 2 quiz. All right, complete the following table. So I've given here the symbols of the elements. So none of these are ions. These are just neutral atoms, okay, neutral elements. See if you can determine for me using your table the number of protons, neutrons, and electrons. Let's check your progress. So in order to fill out this chart, you're going to need your periodic table. And let me share my screen. There we go. So now, how do you fill out this chart? Well, remember that the number of protons is going to be the same as the atomic number. So for sodium, the atomic number is 11, magnesium 12, chlorine 17, neon 10. The number of neutrons, remember that you subtract the mass number, you subtract number of protons from the mass number. So for sodium, it weighs 23, but you subtract the 11 from here and you get 12. And we round to the nearest whole number. So same thing for magnesium, chlorine, and neon. The number of electrons, it's always going to be the same as the number of protons whenever you have a neutral atom. These are all neutral atoms. Remember, ions, like number 4, number 2, they do not have the same number of protons and neutrons. They are not neutral atoms. So ions, just as a reminder, ions are not neutral atoms. So I wanted to start off this morning with a little bit of a review from last time. but also it seemed like we had a lot of heavy vocabulary along with our, learning how to use our periodic table. So let's go on to the new stuff for today. And the new stuff is going to be on page 2.4, or on section 2.3 and 2.4 is our topics today. 2.3 and 2.4. So today's lesson (2.3), which is on molecules, and 2.4, which is about really water and its most unique properties. So if you're following along in your textbook, we are on pages, let's see here. We're on pages 39, and this starts on page 42. All right. So molecules. Well, a molecule by definition this is a compound with two or more nonmetals. So for example, carbon dioxide is a molecule, sorry. Because carbon's a nonmetal and oxygen is a nonmetal. And I think about last time, let me double check my notes. I think I talked about the difference between metals and nonmetals. Did I not? Yes, I did. Just as a reminder, nonmetals live on the right side of the periodic table. So when you're looking at your notes from last time, nonmetals live on the right side of the periodic table. So carbon dioxide is an example of a compound. Oxygen gas, that's an example of a molecule. I keep saying compound, a molecule. And of course, water is an example of a molecule. Now, there are different kinds of molecules. There's what we call a polar molecule. And then we have non-polar molecules. And the difference between them is how they share electrons. The difference between them is how they share electrons. We'll start with something simple. We'll start with something simple like carbon dioxide. When we look at carbon dioxide, if we take carbon by itself, on the periodic table, carbon has 6 electrons. Each oxygen by itself has 8 electrons. So this is how those electrons are arranged in the atom. Here's carbon by itself. Electrons are arranged in layers in the cloud. They're arranged in layers around the nucleus. So I'm just going to represent the nucleus by drawing this symbol in the middle. And now I'm going to represent the cloud by drawing circles, concentric circles, around the symbol for carbon. So the C itself represents the nucleus. This is the first layer in the cloud. This is the second layer in the cloud. Carbon has 6 electrons. So 2 electrons are in the first layer, and then 4 electrons are in the second layer. There's a rule in nature, okay, there's a rule that says when you arrange electrons you can have a max of 2 electrons in the first layer. Then there's a rule that says you can have a max of 8 electrons in the second layer. Carbon only has 6 total electrons, so it's going to have 2 in the first layer, 8 in the second layer, or I'm sorry, 4 in the second layer. When I look at oxygen by itself, similar arrangement. Okay, that's the nucleus, 2 in the first layer, and then it has 6 in the outer layer. So 6 electrons in the outer layer. The outermost layer for any atom is called the valence layer, or sometimes we call it the valence shell. So the electrons that you find in the valence shell are called valence electrons. So we say that oxygen has 6 valence electrons. Carbon has 4 valence electrons. Neither carbon nor oxygen is chemically satisfied because they both want to have 8. This is the magic number in the outermost layer, is 8, at least for the outermost layer that we're worried about. So he needs 4 more. He needs 2 more in order to achieve this magic number 8. So what happens between carbon and oxygen atoms so that they can achieve stability, or so that they can achieve that magic number of 8? Well, if we take that 1 carbon, whoops, and 2 oxygen atoms, and I arrange them like this, here's carbon with its 2, and then 1, 2, 3, 4. And then I draw next to it oxygen. Here it is with this 2. There we go. 1, 2, 3, 4, 5, 6. Now I'm going to do the same thing over here. I'm going to draw my big circle first, my smaller circle, then my inner circle, my 0. 1, 2. All right, I'll let you finish your drawing. Let you finish your drawing there. While I'm pulling up the PowerPoint for today. So when we look at our diagram, what I did was I drew oxygen, and I drew the other oxygen with carbon in the middle, but I kind of pushed them together. And if you count the red dots, which is my oxygen, I still have 1, 2, 3, 4, 5, 6. Where did I get all these 7, 8s from? Oops, I got too many. You know what? I just realized I drew my picture wrong. Holy cow, I totally drew that wrong. Let me do it this way. Sorry, after you draw that diagram, and then I drew it wrong. I was more worried about lining up my circles than I did line them up correctly. Okay, let's do this. 1, how am I gonna draw this? Let me think here. Okay, like that. There we go. That's better. That's a big oops. Don't study this. So don't study that diagram. And then there we go. Much better. Okay. My other diagram was prettier, but it wasn't right. There we go. Okay, much better. So here's what I'm trying to show. Here's what I'm trying to show. When I look at oxygen, it brought with it its original 6 valence electrons. Well, let me catch up. Give me a number 1 when you have finished your diagram. So here's what we're trying to show. Each oxygen brings 6 valence electrons. Oops, valence electrons. That's 2 away from 8. It needs 2 to be satisfied. So in order to be satisfied, it will actually share with carbon some electrons. And so now the red dots are 1, 2, 3, 4, 5, 6 of oxygen, but it's sharing the blue ones with carbons. So it shares electrons with carbon to achieve what we call the octet, or 8 valence electrons. So if I examine just this part of the molecule, now I can see that oxygen has the 8 in the outermost shell, 2, 4, 6, 8. It brought its own 6, but it's sharing 2 of them with carbon. The other side of the molecule is doing the same thing. There's 2, 4, 5, 6 originals, plus the ones that it's sharing with carbon. At the same time, the carbon brings its 4 valence electrons and needs 4 more to achieve octet, i.e. the octet. And it does so by sharing with each oxygen atom. So if you look at carbon in its outermost shell, it has its own 4, and then it's using the 4 that the 2 oxygens brought to get its 1, 2, or 2, 4, 6, 8. And so now everybody in this diagram is happy. The type of chemical bond that occurs by this sharing business, that is called a covalent bond. Covalent bonds share electrons, and you find them most commonly when you have a nonmetal bound to another nonmetal. Nonmetals have a tendency to share electrons and form what we call covalent bonds. So a covalent bond is one where electrons are shared. And we share those electrons so that the atoms that are involved in the bond can achieve the octet, which is 8 valence electrons. Now, the problem with covalent bonds, or I shouldn't say the problem, but there's two different kinds of covalent bonds. There's two different kinds of covalent bonds. There are those polar covalent bonds, and then there are non-polar covalent bonds. So electrons are not always shared equally. So just because there's some sharing going on, it doesn't necessarily mean that those electrons are shared equally. In other words, carbon and oxygen may or may not play nice, and they may or may not share electrons equally. So that's why there are two different types of covalent bonds. When you have a polar covalent bond, the electrons are shared unequally. And it creates an area on the molecule with a slight positive charge. And the way we show that is we draw the Greek letter delta, positive, and then an area on the molecule with a slight negative charge. And we show that with a delta negative. In a nonpolar covalent bond, electrons are shared equally. So a good example of something that is polar versus nonpolar, well, carbon dioxide is a nonpolar covalent compound. A simple way to represent our elaborate drawing is just to do this business. Okay. Carbon dioxide has two double bonds. Each bond is 2 electrons, so there are 2 4 electrons being shared here, 2 4 being shared there. When you look at the compound, and if you kind of, divide it in half, one half of the molecule is equal to the other half. And so you have a force of oxygen pulling on carbon, and then you have another force of oxygen pulling on carbon, and there's equal force pulling in opposite directions. Nobody wins the tug of war. Oxygen is a larger molecule or larger atom as compared to carbon. And so oxygen wants to pull the electrons that are shared closer to it, but it cannot because there's another oxygen on the other side that's pulling with equal strength or equal force. So nobody wins the tug of war. So as a result, the electrons that we share are shared equally. So this is a non-polar covalent compound. When we look at polar compounds, the best example of what is a polar compound is good old water. Good old water is a great example of a polar compound. So we'll draw a water molecule. Here's our oxygen. first circle. Okay. So here he is with his 2 inner electrons. And remember, he has 6 on the outside. 1, 2, 3, 4, 5, 6. And then hydrogen only has 1 electron apiece. And so he usually bonds just like this. So here's a simplified arrangement of our oxygen atom, our water molecule. So we have our oxygen in the middle, and then the hydrogen is on the 2 sides. Well, the chemistry of this molecule makes the shape of this molecule more like, and I promise I'm not making this up, more like a Mickey Mouse head. So if I draw it here on the side, here's my hydrogen. Here's my hydrogen. And I'm going to draw the shared electrons here. Okay, so the chemistry of this molecule, if I was to simplify this, what happens is that these 2 hydrogens kind of come on one side of the molecule, and these 2 pair of electrons that are not bonded to anything, they kind of pop over on the other side of the molecule. So you end up with something that looks like this. Okay. You end up with something that looks like that. So these guys kind of come around this way, and the 2 unpaired sets go over here. This is still my oxygen atom right here in the middle. And this arrangement does something kind of interesting. Oxygen and hydrogen are not the same size of atom. Oxygen is much, much bigger than hydrogen. Much, much bigger. And so even though they are sharing electrons right here, they don't share them equally. Oxygen is a little greedy, and it pulls the shared electrons towards itself. The same thing is happening here. Oxygen's a much, much bigger atom than hydrogen, and it pulls those electrons a little bit closer to itself. So remember that electrons have a negative charge. So you have these 2 sets of unpaired electrons that are negatively charged, plus this guy's pulling shared electrons closer to itself. So you end up having this side of the molecule with a slight negative charge, because most of the electron charge is on that side of the atom, of the molecule. What you leave behind is a slight positive charge on each of the hydrogen atoms. So this is what we mean by a polar covalent bond. Things are shared, but they're shared unequally. So you have a slight positive pole, and you have a slight negative pole. And polar means that you have 2 oppositely charged areas or 2 opposite poles on that molecule. So water is a great example of a polar covalent compound. Now, why is this important in biology? Why is this important? Well, we're going to find out that a lot of what determines how things get in and out of the cell, whether it's easily brought into the cell or it's a little bit hard to get something into the cell, has to do with polarity. There is a adage, there's a little saying in chemistry, like dissolves like. So polar compounds mix with polar compounds. But nonpolar only mix with other nonpolar. Nonpolar and polar doesn't mix. This is why oil and water don't mix. Oil is nonpolar, oil is nonpolar and water is polar. So if something mixes with water, it's a polar compound. If something mixes with oil, it's a nonpolar compound. And we'll find out, especially in our next lecture, that there are things that are polar and things that are nonpolar that make up living substances. And the whole way that things either stick together or how things mix or don't mix has to do a lot with their polarity, whether something is polar or versus nonpolar. So you can use as an example, oil as being nonpolar, whereas water is the example of polar substances. So if something mixes with water, another solution mixes with water, then it's a polar solution. But if it mixes with oil, then it's a nonpolar solution. Oil and water don't mix because, well, they have different polarities. Oil is more like carbon dioxide and it shares electrons equally, whereas water is the classic example of a nonpolar compound. I know this is a detailed drawing, so type a number 1 when I can move on to the next page. All right, you're keeping up well, good. So again, why is water's polarity, why is it so important? And this is where I'm going to skip over to section 4. I'm going to skip over to section 4 when I talk about water and its properties. So if you're following along, I have skipped on to page 42. I'm going to go back to something from chapter or section 3 in a little bit, but this is a nice segue into water and its properties. So water is, even though it's so common to us, we just think, oh, it's just water. Water has some properties that nothing else has, or at least the combination of its properties, I should say, are very unique based on its size. Water is a relatively small compound, yet it has some pretty interesting properties for being such a lightweight, so to speak. And all of the properties that we're going to discuss, all of the properties result because water is a polar compound. So because water is a polar compound, everything that we talk about is a result of water being that polar compound. So we'll draw our water molecule again, just so that we remember what it means to be polar. And so we'll have our hydrogens here, and our oxygen's kind of the big part. And we'll label our hydrogens slightly negative. And we'll label our oxygen slightly positive. Oh, slightly negative. Our hydrogens are slightly positive, sorry. There we go. So our hydrogens are slightly positive, our oxygen is slightly negative. And that's what we mean by a polar compound, is that we have two oppositely charged poles on this. So one of the things about water, and I'm going to change the terminology in your book, but water has a high heat capacity. Your book doesn't call it this, but I'm going to call it that. Water has a high heat capacity. And what heat capacity is the amount of energy that you absorb before you change temperature. Water has a high heat capacity, and heat capacity is how much energy can you absorb before you actually change temperature. What your book says is that water stores heat. It's another way of thinking about it. Water stores heat. Water has the ability to absorb, I cannot spell today, absorb and store heat without changing temperature. That's crazy, because we always think of like heat and temperature as being the same thing, and it's really not. It's really not. Heat, by the way, is energy. Heat is energy. Temperature is heat intensity. So for example, let's say I have this sounds like a funny number, but I promise it's not. Let's say I have about 20 grams or about 20 mils of water. Let's say I have about 20 mils of water. And that's not very much. That's less than a tablespoon. So about a little bit less than 1 tablespoon. So it's a little bit less than 1 tablespoon. And it's sitting at 20 degrees Celsius. Okay. So I have a small amount of water. It's sitting at 20 degrees Celsius. If I want to raise the temperature to 21 degrees Celsius, I must apply 4.184 joules of energy. Okay. I must apply 4.184 joules of energy. So why I'm telling you this is to kind of give you the difference between heat and energy, okay? Or temperature and energy. This is my temperature. This is my energy. This is my energy. So when I talk about heat and energy, it's not exactly the same thing. Temperature measures heat intensity, and in this case, I'm applying 4.184 joules of energy. If I apply less than that, the temperature doesn't change. So if I apply only 4 joules of energy, the temperature remains at 20 degrees Celsius. This is what we mean by water has the ability to store heat. So if I apply less than this 4.184 joules of energy, the temperature does not change. In essence, I can use the water to store that energy that I've put into the water. So I'll write that out. Okay. So you can put heat into something without causing actually the temperature to change. Water, for its size, I don't want to say like water, what's a good way to describe it? Water has a unique ability of being able to absorb a lot of energy before it changes temperature. Most other substances that are about as big as water, they cannot absorb as much heat as water can. They have lower heat capacities. But for its relative size, which is 18 atomic mass units, because you've got 1 oxygen, which weighs 16, and 2 hydrogens, which weigh 1 apiece. So for its size, water has a really high heat capacity. In other words, it has an incredible ability to absorb heat without changing temperature. Most other molecules that are about the same size of water cannot do it as well as water can. They have a much lower heat capacity. So yes, water can store heat, but it stores a lot of heat before it changes temperature. That's what we mean by high heat capacity. Now, why is that important to living things? What do you think helps regulate your own body temperature? What compound do you have a lot of circulating inside of you? I'll give you a hint. Water. What do you use to cool off? Well, you use water. Because when you perspire, you form water on the surface of your skin. Well, if that water evaporates, when it leaves, it takes the heat with it. So if you are heating up perspiration on the surface of your skin, you are actually using water to cool you. So in other words, the perspiration on the surface of your skin, before it evaporates, it's going to have to absorb a lot of energy. And when it does absorb that energy and becomes a vapor or it evaporates, it takes the energy with it. This makes water an effective body temperature regulating mechanism. Especially when it comes to cooling via perspiration. So one of the ways that you maintain your homeostasis is through perspiration. And when you perspiration, there we go. When you perspire, when that water evaporates off the surface of your skin, well, the heat goes with it. How much heat? Well, about 4.184 joules for roughly every 20 mils that you produce. That's a lot of energy. Trust me, that's a lot of energy. Besides perspiring, another way that you shed heat is every time you exhale. Because every time you give off carbon dioxide in your breath, mixed with it is a tremendous amount of water. So if you've ever, breathe like that on something like a glass or a mirror, the mirror fogs up or the glass fogs up, that fog is due to the heat coming off in your breath. So exhalation is another way that you give off heat. You might know that dogs don't really have the ability to perspire, but one of the ways that dogs do give off heat is they pant. So if you've ever seen a dog panting, they're giving off excess heat through their breath. All right, let's go on to the next one. Also on page 42, they talk about water forming ice. And really, this is what they mean. So yes, water forms ice. But ice, and this is the real part that I think that they're trying to emphasize, ice is less dense versus liquid water. Ice is less dense than liquid water. Ice is less dense than liquid water. So here's what happens. When you have these water molecules, when you have all these water molecules, and I'm drawing them, several of them here. The hydrogen in one water molecule is attracted to the oxygen in the other water molecule. So you have these little attractions going on like this. So when these molecules start to get closer and closer together to form ice, What it actually does is it creates pockets of air inside the forming ice crystal. So those pockets of air is what makes ice less dense. So just as an example, the density of water at roughly 20 degrees Celsius, water has a density close to 1 of about 1 gram per ml. At around 0 degrees Celsius, and I'm going to look up the number because I don't want to mislead you. The density of ice is about, it depends on the exact temperature, but somewhere around 0.9. So you go from 1 to 0.9. It doesn't seem like a big difference, but because the density of ice at 0.9 grams per mil is less versus water at 1 gram per mil, ice floats. Because if you're going to sink, you have to be bigger than 1 if you're going to sink in water. So if you think of all of the animals, especially in polar regions, they depend on ice islands, ice bridges, in order to live out really part of their life cycle. Maybe when they swim out to sea to go fishing. You probably heard about the polar bears. The ice caps are becoming smaller and smaller, and there's less and less ice islands out there. So polar bears can swim a tremendous distance, I mean miles. They can swim a tremendous distance in order to look for food, but they have to have a place to rest. It's possible that as they're looking for food, they become so exhausted, there's no place for them to rest, and they literally drown out at sea. Ice islands and ice bridges are also important for like penguins, and in some cases seals, because they will bear their young on these islands and they'll let them grow there so that they're far away from other predators. If there's no place for you to, leave your babies, where are you going to raise your young? How are you going to get from one location to another if there is no ice bridge available there? So, the formation of ice is tremendously important to animals living in polar regions. I have a diagram. I'm going to share this diagram with you. This is from your textbook. This is from your textbook that shows the density of ice being less than the density of regular water. Here we go. Oops, I think I shared the wrong thing. Okay, there you go. So here's the diagram in your book. And here is the example that we were trying to draw out. The book does it a little better, but if you notice here, here's all the water molecules, but as they become locked into place, here is the air pocket I was talking about. Here's the air pocket that forms inside of the ice crystal. So this is what reduces the density or reduces the mass, in a sense, of the solid ice as compared to the liquid water. Last two things, I'm watching the time here. Oh, Water evaporates. This is kind of related to heat capacity, but one thing that they left out, I wish they would have said it this way. Oh, they kind of did. Where they say water clings. Oh, hold on, you can't see what I'm writing. There we go. So your book says water clings. We're going to change this to water exhibits cohesion and adhesion. Water exhibits cohesion and adhesion. Cohesion means that water sticks to itself. Adhesion means water sticks to a surface. So cohesion is water sticks to itself. Adhesion means water sticks to a surface. And this is kind of like our diagram for ice. We'll simplify our diagram here. We'll just draw two molecules. Between the hydrogens that are slightly positive and between the oxygen that's slightly negative, you have a force right here, and that force is referred to as a hydrogen bond. Water molecules have a tendency to form tons and tons of hydrogen bonds, and it always happens between the hydrogen of one molecule and the oxygen of a separate molecule. These, by the way, up here, these are all hydrogen bonds as well. Now, the interesting thing about this hydrogen bond is that this is why we say that water molecules are cohesive, that they stick to themselves. So in other words, water is naturally attracted to itself. As a result, water has what we call surface tension. Water exhibits an amount of surface tension. So if you look at the surface of a body of water, those water molecules, they are stretched like the skin of a drum. They are stretched very tight because the water molecules are all pulling on each other. This is what allows small bugs to walk on water. So how do they do that? It's not so much that just because they don't weigh very much, but it's also because they distribute their weight in such a way that they can make use of the water's surface tension. That's supposed to be a bug. I'm not a great artist, but that's supposed to be a bug. When we talk about water's adhesiveness, okay. So when we talk about adhesion, and we'll draw our water molecule again, we'll just draw one this time. Let's say our water molecule is inside of a tube. If you have a negatively charged surface, the water molecule is going to be attracted to that negatively charged surface. So water is attracted to any slight charge in a surface. If the surface is positively charged, then the water molecule turns itself around so that the negative part is attracted. If the water molecule, if the surface is positively charged, well, then it's oriented this way. So it's really kind of like the perfect arrangement. Whatever charge the surface might have, the water molecule can be attracted to it. That's what we mean by adhesion. Water likes to stick to surfaces. If you put adhesion and cohesion together, then water exhibits what's called capillary action. This is adhesion and cohesion together. What capillary action is the ability to climb thin tubes. This is especially important for things like trees and other plants. Trees and plants in general, they have to get water all the way down from their very roots, all the way up to the very most upper leaf in the canopy. Well, trees do not have hearts, so how are they going to pump water? Well, they don't actually have to exhibit any energy to pump water. Trees are actually a bunch of straws that are all put together. And so trees have many, many tiny, thin tubes, which the water actually climbs up itself because the water molecules are attracted to each other, and at the same time, they're attracted to the surface. Hold on, my dogs.
Mrs. Weir. You're still muted, so we can't hear you.
Thank you. Sorry, I was yelling at my dogs. I didn't want y'all to hear me yelling at my dogs. This is the last thing. Water is important in the pH scale. Water auto-ionizes, or it breaks apart by itself into the hydrogen ion and the hydroxide ion. This is the one that we use for the pH scale. And so you're probably familiar with the pH scale, and that it's based on the number 1 to 14. Anything above 7 is considered a base or alkaline. Anything below 7 is considered an acid. If you are exactly 7, you're considered neutral. You're not an acid, you're not a base. The further you get from 7, the stronger you are an acid, or the stronger you are a base. The closer you get to 7, the weaker an acid, the weaker the base. Now, if we were in a chemistry class, I would have you learn to calculate pH. I'm not going to make y'all calculate pH, but you do need to interpret pH. Okay. So you don't have to calculate it, but you need to interpret it. So let's say you're going to compare two pH values, like a pH of 4 versus a pH of 6. Okay. What they have in common is that they are both acidic. But the pH of 4 is stronger versus the pH of 6. So 4 would be a stronger acid as compared to a pH of 6. So here's my question. How much stronger is pH of 4 versus pH of 6? And this is what I mean by interpreting, knowing that they're both acids, knowing that one is stronger than the other. And lastly, how much stronger? Okay, this is not meant to be a trick question. But 4, here's the answer. pH of 4 is 100 times stronger versus a pH of 6. So how do you know? Well, each whole unit on the pH scale is a power of 10. So I know that 6 minus 4 equals 2, right? So then you would take that 2 and raise 10 to the second power, which is the same thing as 10 times 10, which is the same thing as 100. So the difference between 4 and 6, I understand it's a value of 2, but it's 2 to the 10th or 10 to the second power, which is the same thing as a value of 10. So you might see a question on the quiz about how do you interpret pHs. You need to know which is an acid, which is a base, and how you interpret whole numbers. I am right up against the time, so I'm going to stop for right now. I'm going to stop recording because I'm going to talk about lab a little bit. But I'm going to stop recording.